When it comes to Newton's third law of motion, you might have heard it stated that for every action, there's an equal and opposite reaction. I don't prefer to state Newton's law in that manner because it's often overextended beyond laws of motion, right? Some people argue because of Newton's third law that if you're friendly to your neighbor, they'll be friendly back toward you. Okay, so it's certainly not a law about social behavior. I think maybe the best way to state Newton's third law goes something like this. All forces come in pairs. That's probably good enough. In other words, it's not possible for a bat to hit a ball without the ball hitting the bat. It's not possible for a hammer to hit a nail without the nail hitting the hammer. On and on we go. When a deer runs out into the road, the car doesn't just hit the deer also hits the car. When the Earth pulls on the moon pulls back on the Earth. So then that begs the question, which gets the brunt of the force? Which gets hit harder, the hammer or the nail? Some people argue the nail because it's the one that gets driven into the wood. Some people argue the ball gets hit harder than the bat because it's the one that goes flying into the outfield. But we need to add a little more information to this statement of Newton's third law. All forces do indeed come in pairs, but there's a couple facts about those pairs. One says if we called the bat object A and the ball object B, the force that object A exerts onto object B is equal in magnitude to the force that object B exerts back onto object A. Now it's equal in magnitude, but since force is a vector, we're going to indicate that, and to say that it's in the opposite direction, we can just put a negative sign. So there's a little detail about these force pairs. They're equal and opposite, meaning equal in magnitude and opposite in direction. So the ball feels a force in this direction, the bat feels a force back in this direction. Which one is greater? Well, I've drawn those two in the same length to illustrate the idea that they're equal in magnitude. This would be the force that A is exerting onto B. This would be the force that B is exerting back onto A. So notice that the two forces do not act on the same object. One force is exclusively on the ball, and the other is on the bat. Okay, which gets pulled harder due to the force of gravity, the Earth or the moon? There's the moon. There's the Earth. The Earth is pulling, oops, wrong direction. The Earth is pulling on the moon. So we can say this is the force of the Earth on the moon. At the same time, the moon is pulling on the Earth. Those two forces are equal in magnitude, clearly opposite in direction. One is labeled FEM for the force of the Earth on the moon. The other is FME, the force of the moon on the Earth. Okay, well, this leads to a common misconception, and it's illustrated in the form of this cartoon. So there's a farmer that tells his horse that he wants to get going to bring his goods to the market, and this horse starts talking back. He says, "Why bother? It's going to be a futile effort." And the horse goes on to try to explain Newton's laws of motion to the farmer. He says, if I pull forward on the cart's going to pull back on me. That's known as Newton's third law. So the forces aren't just in pairs, but they happen to be equal and opposite. We have two forces equal in magnitude pulling in opposite directions, so they're going to cancel each other out. That's going to create for a zero net amount of force, so we'll never get moving. Now that can't be the case, right? Newton's third law can't lead to this argument that nothing ever moves. So I believe what the horse is saying is there's a forward force. This is the force of the horse on the cart, but at the same time there's got to be an equal and opposite force, the force of the cart back on the horse. Yeah, if they're equal in magnitude and opposite in direction, don't they just cancel each other out and the acceleration is equal to zero? This gets the farmer thinking a little bit. considers Newton's laws of motion, in particular Newton's second law, and argues back to the horse that he doesn't care about the forces exerted on the horse. All the farmer cares about is what amount of force is acting on the cart. As long as the cart moves, he's good to go. Okay? So the horse comes back and continues his argument. How could he move forward if the cart pulls backward on him? So now I think the problem is the horse isn't taking into consideration all of the forces that are acting. What we really need are some free body diagrams, right? So let's make a dot right here to represent this horse. And let's make a dot right here to represent this cart. So what are all the forces acting on the cart? Well, these forces that I identified earlier are going to appear in these free body diagrams, but they're not going to appear on the same free body diagram. See, that's another key about the pairs associated with Newton's second law. One, they're equal and opposite, and two, perhaps more importantly, they never, ever, ever act on the same object. One force is on the ball, one is on the bat. One force acts on the hammer, the other acts on the nail. One force acts on the deer, the other acts on the car. If they're not acting on the same object, then they don't have the opportunity to cancel out. So let's show the forces acting on the cart. In the forward direction, this is the force of the horse on the cart. There's also an upward normal force. There's a downward weight vector. Those are almost going to certainly cancel each other out. And by the way, just because forces happen to be equal in magnitude and pointing in opposite direction does not mean that they constitute a third law pair. The normal force from the ground and the weight of the cart do indeed point in opposite directions and cancel each other out, but they're not a third law pair. Another name for the normal force is the force of the ground acting up on the cart, and the weight is the force of the center of the earth pulling down on the cart. Okay, so actually the third law pair to the normal force, if the ground pushes up on the cart pushes down on the ground. And notice we're not making a free body diagram for the ground, all right? Okay, is there some backward force as well? Yeah, maybe there's a little bit of what we call rolling friction, pulling backward, but thank goodness whoever built this was wise enough to put wheels on the cart and horseshoes on the horse's feet. If it was the other way around, if there were horseshoes on the bottom of the cart and wheels on the horse's feet, yeah, it probably wouldn't get moving. Okay, so here's where we see Newton's third law. If there's the force of the horse on the cart pulling forward, there's a force just as big pointing in the opposite direction that we label as the force of the cart on the horse. Fortunately, there's an even bigger force in the forward direction acting on the horse, and that's thanks to the horseshoes that he's wearing. This is the force of friction at the ground. And then there's also, for the horse, some normal force and some weight, but these cancel out. Okay, so yeah, it appears then that there's some net force acting on the cart, right? As long as the forward force is greater than the friction, and for the cart, friction is reduced by putting wheels on it. For the horse, there's a forward force that's greater than the backward force, thanks to the increased friction due to the horseshoes. So we see that this force here, the force of the cart on the horse, is indeed equal and opposite to the force of the horse on the cart, but because they're acting on two separate objects, they do not cancel each other out. Okay, so in the final slide, you see that the farmer's happy and everything goes according to plan. So that's right. All forces come in pairs. Those pairs are equal and opposite, and they never act on the same object. Thanks for watching.